Swayam Prabha. Digital India. Educated India.
Dear friends, welcome back. We have been discussing about the graphical modeling techniques used in system engineering. In the last two classes, we discussed about the data modeling and process modeling, and we saw a few methods of data modeling and process modeling, and we saw a few examples also how these methods can be used for designing of engineering systems, or how these modeling techniques can be used for modeling of the system, especially when the data flow, the relationships, the process relationships, process flow data, the relationship between various functions, and then the interaction between these functions. Today we will discuss about the behavior modeling. Behavior modeling, one of the modeling method we need to do, because we have data modeling, process modeling, and the third one is behavior modeling. In behavior modeling, we use the method of behavior modeling for modeling the dynamics of the system. So we want to see how the engineering system works, or what is the dynamics of the engineering system, how the control actions are taking place, how the particular incidences are triggered, or how a particular incident stops or particular function stops and the next function starts. So all these kinds of dynamics of the system can be modeled using behavior modeling techniques. Here the control, activation and termination of system functions are basically modeled using the behavior model. So not only the data and the process, we want to model the control, the activation and termination of system functions, and for this purpose we have various methods, and one method is known as function flow block diagram, that is FFBD, and we have other things like behavior diagrams and Petri nets. So we will see some of these methods and then try to understand how these methods can be used for modeling the behavior of systems, or how the dynamics of the system can be modeled using behavior diagrams. So we will take the FFBD first, that is the function flow block diagram, and then see how to use this function flow block diagram and then model the behavior. So the FFBDs, they provide a hierarchical decomposition of the system function and show a control structure that dictates the order in which the function can be executed at each level of the decomposition. So that is the importance of FFBD. We can actually show the control structure that actually dictates the order in which the functions are executed and the various level of decomposition. So there are different ways of executing the function. They are basically classified into four categories. One is the series execution, the other one is the concurrent execution, and then the selection and multiple exit. So these are the ways in which the functions can be executed in a system. So we will see how do we actually model these kind of behaviors, that is a series behavior or concurrent behavior, or exit and the selection and exit procedure. So how do we actually model this using FFBD? We will take a few examples and then show the method by which we can do this. So in series structure, what we are having is, as the name suggests, the functions will actually execute in a serial way. So as you can see here, there may be different functions. So we will start with a reference function, which is maybe an external function or a function of a subsystem. So from that reference we will have the one function executed, and then it will go to the next function that is executed, and then it will go to the external system or the other subsystem. So this is a serial execution. As the name suggests, the functions will be executed in a serial way. For example, you can see that if you take the system design activities, then we will say perform system design activity. So once we complete such system design activities, then only we go for the integration activity. So perform integration. Again it appears to be a very simple case, because we are telling something which is very obvious, but this is the way how we actually show the series execution of functions in the function flow block diagram. So we will complete this function and then go to the next function, that is the serial execution of the functions. And in the concurrent, or sometimes it is known as parallel also, in concurrent execution we will be having the same referent function, and then we will be having two functions executing at the same time, two or more function executing, and it is shown by a block AND block, and in this AND block we will be connecting all the other functions, and here we will be having the concurrent functions listed. And again once it is completed, the next function can start only after the completion of all these functions, all these processes or the functions, and then it will go to the reference function or the external function. This is the concurrent or parallel execution. So here again you can have examples like system level design. Suppose if you take the same system engineering, then it is system level design, then you have the subsystem level design, subsystem level, and then component level. So we know that if you want to execute all these functions, we need to have a, this all need to be done concurrently or parallelly. So after that end of this design process only we can go for the testing or integration of the components. So we need to do all this in a concurrent way or in a parallel way, and once we complete all this design, then only go to the next function, that is the concurrent behavior of the functions. So this need to be done parallelly or concurrently, and once all these are completed, then only it will go out. So this AND shows that all these three inputs should be there for this to go to the next function, that is here the AND represents all this, it should be there, this AND represents all this will go happen at the same time. So when this input is coming, all the three output will go concurrently, and here all these three inputs should be there for the next function to execute. That is the concurrent behavior of the system. The next one is the selection structure and multiple exit. In selection structure and multiple exit, it actually will be having series functions, it may be having concurrent functions, and it may be having some selection that you can actually select one of the functions, and you can have multiple exits or iterations also. So here again we will take a case of system design. So if I take perform system design as a function, now I will be having many iterations of the system design or the system, because there may be some kind of repetitions, or we will represent these iterations by a block IT, and then there may be some loops through which it will be going, and that is represented by the loop LP. I will explain how these are actually coming into the behavior. And once we complete this system design, we need to have the testing. So that is a testing function. So inspection and testing, and after the inspection and testing there are options like some of the components may pass the inspection, some of the components may fail the inspection. So we need to select these two options, and one of the options need to be chosen from the multiple options available. So what we do, we have these two options here. So one will go for the selected one, that is passed one, and the other one will go to the which are actually rejected, or it is not passing the inspection. So the cleared system will just go directly to the same main loop, and again it will start from here to the next function. So we will see what actually happened to this one. This is the accepted, so we are selecting accepted one and rejected or with some deviation from the required specifications, and here we can actually do a fixing of the problem. So you fix the problem and again send it for here. So once you fix it, there are two options, one is that it is acceptable, one is it cannot be accepted. So the small fixing can be done here, the rejected components can be fixed here itself, and once it is fixed we can actually either take it, accept it or reject it. Accept or reject one, and if it is rejected we need to actually have a redesign. So this is redesign, so the rejected one has to go redesign and then it will come here. So now we know that there may be this rejected component may go through this or through this route, and any of these routes is acceptable. So this is an OR block, so we can actually any one of these component comes here, it has to go to the next level. So it need not be, though there are parallel activities, so you need not wait for the both to happen. So any one of these happens, it can go to the next level, and then so this also will come here. So now we have components coming from both. So from the inspection the accepted will come directly and the rejected one may go for redesign or may get accepted, and it will come here and it will go to the next level. So here it is an OR loop, so any one of these will come here. So you can see from the inspection there are two options, so one of these option go directly, another option will go through different processes and finally come here to the this block, and then here we will be having a looping. If there is a deficiency fixed, then it has to go to this loop again for the inspection. So some of the components will come through this, so there was a deficiency and it was fixed and it is coming over here. So we need to make sure that if it is coming through this loop, then it has to go back again and then do the inspection and testing and see whether it is actually passing this test or not. If it is passing this test, again it will come through this, and once this is completed it will go to the next level where integration to next subsystem. This is integration, this integration to next subsystem, and then we will be having, that is one subsystem, then we will be having a iteration. This is for the next subsystem design. So this is for next subsystem, and then it will go out from here to the next function. So this is a selection and multiple exit structure. So this is the loop for if deficiency is fixed. So if the deficiency is fixed, then a looping will be there, and this is for each subsystem this process will do. So for each subsystem we need to complete the same procedure, that is why there is an iteration loop, as an iteration, and this is the looping, because if something is fixed over here, there was a deficiency in one of the components or subsystems, then that will go through another process where the fixing will be done, and then again it has to go for the testing. So that is why it is come back and then do inspection and testing, and if it is accepted it will go out and then come to the integration, and then again we will be doing the same process for the other subsystems also. So we will be having many subsystem, when system design is complete we will be having many subsystems. So for each subsystem we will do the inspection and testing, and if it is accepted it will go out to this block, if it is not accepted it will go through this loop to fix the deficiencies, and if it is accepted it will go, if it is not accepted it will go for redesign, and whenever there is coming from this loop, this output is coming from this loop, then this will go for the inspection again and pass, and once everything is passed through this, it will go for the integration, and once the integration of that subsystem is completed, then this loop will again repeat, because the next subsystem will be taken for inspection, and so on it will continue. So we can see here we are actually using many blocks here, an iteration, looping, and then of course the OR and OR also can be used, and in some cases we may have to use AND also. So in this case there is no AND block, but here we have an OR block, so one of these output will be coming out. If both the outputs are needed some situations, then we have to use the AND block as shown here in this block. So we have used the OR block there, but some cases we may have to use AND block also. So this is the selection structure and multiple exits. So in FFBDs, that is in the function flow block diagrams, we have series execution, we have concurrent execution, and we have selection structure and multiple exit. So any of these methods or a combination of these can be used for representing the actual design of a system or actual behavior of a system. So some subsystem we may have to model the behavior of the subsystem using this method. So we can actually use the series, concurrent, or selection and multiple exit, or a combination of these to represent the dynamics of the system. Let me take an example and then show how it is actually done. We will take an example of the auto link system what we discussed in the previous class. So in the auto link system we will see how the functions can be represented, or how the dynamics can be represented using the FFBD. So we will take a reference function or an external system or a previous subsystem, and then see what are the concurrent activities to be carried out. So there are many concurrent activities to be carried out in the auto link system. So we will see that there are parallel functions to be executed. So this is the navigation activities. This is the itinerary of the passenger or the person who is using the system, and this is the vehicle condition function, basically looking at the status of the vehicle. Customer support. So these are the 4 functions need to be executed parallelly in order to provide a required service to the passenger or the person who is using auto link system. If we need to provide the required service like knowing the location, or in an emergency providing the support, all these parallel functions should be executed. So what are these functions? We will write down those functions here. Basically we will be looking at the latitude and longitude calculation, latitude, longitude, and then integrating the current position with the map. So integrate current position, because we get the latitude and longitude. Once you get this, you can actually integrate the current position with the map. That will help the passenger for the navigation, or the driver for navigation, and that is the required for navigation purpose. And then here we have to calculate the display route based on the input given by the user. He will be giving the itinerary where he wants to go, and once that information is obtained, the route has to be calculated using a database, and then the present latitude and longitude will be calculated, and based on that a map will be generated to show where he is at present. And then vehicle condition need to be assessed, because if the vehicle is in good condition or not needs to be assessed to help the user. So vehicle condition or vehicle status or vehicle health status. So vehicle health status need to be assessed, and then the customer support for so we need to identify the client who is actually using it, whether he is authorized to use the system or not. So identify the client, assess the sensor data, basically whether all the sensors are working properly and whether GPS data is correct. So this kind of information to be collected. So assess sensor data, and then if needed contact emergency. Contact emergency services, that is contact emergency, and all these need to be executed concurrently in order to provide the service. So that is the outputs. So here you can see, in this case the auto link system, a customer or a driver wants to get some assistance from the auto link system for his navigation purpose or his emergency response, whatever the situation is. So in this case the auto link system should execute all these functions in a concurrent way, then only he will be able to, the system will be able to provide the necessary output. So the functions need to be provided are the navigation assistance, the itinerary especially to calculate the route, the condition of the vehicle, whether the vehicle is in good condition, and then the customer support in various ways, like the client is an authorized person and whether all the data systems are functioning properly and whether the emergency service can be provided. This need to be in a serial way, so all these functions are executed in a serial way, as you can see here. Here also this has to be done in a serial way. So you generate the latitude and longitude data and then integrate that with the current position with the map. So that will help the user to navigate himself, and then this is to calculate the routes. If the user gives his itinerary, the route can be calculated, and this can actually be, once the route is calculated and this position is known, that can actually be given to the passenger or the user. So that actually we need these two for the outputs. Similarly we need to know the vehicle condition and the other customer support services. So all these are provided, and once we have all this information, then an output can be given to the customer to use the facility. So that is the way how we actually represent the behavior of the system using FFBD. So we are using the FFBD, that is the functional flow block diagram, to represent the dynamic behavior. So that is an example for the auto link system, and how do we use the function flow block diagram to represent the dynamics of auto link system. This was an example for the function flow block diagram, and the next method is, we have this method called Petri net. So Petri net is also a method used for modeling the dynamics of the system, that is how the input output can be controlled, how the concurrent activation as well as the status of different functions, and how do we actually start a particular process, or what are the conditions under which a process can be started. All these can be represented using Petri nets. So as you can see here, the Petri net was introduced by Carl Adam Petri in 1962, which is a diagrammatic tool to model concurrency and synchronization in distributed system. So we saw the concurrency of systems, but then in some cases we need concurrency as well as synchronization. For example, if you take the traffic light on the roads, we need to have some kind of a synchronization between the other lights. When you have a junction, we will be having multiple traffic light, so we need to have some kind of a synchronization between this traffic light. So how do we actually represent that kind of synchronization and concurrency? That can actually be done using Petri nets, and then used as a visual communication aid to model the system behavior. So as you know, this is a graphical tool, so it actually helps as a visual aid to show the synchronization. And of course there are strong mathematical foundation for these methods, and it actually captures the precedence relations and structural interactions of potentially concurrent and asynchronous events. So it actually captures the precedence relations. So what is the precedence, which function should precede or succeed a particular process. So that actually this Petri net captures that precedence relationship, and structural interactions of potentially concurrent and asynchronous events. So there may be asynchronous events, so we will actually able to capture the structural interaction between these events using Petri nets. We will see how to develop the Petri net. So Petri net has got few basic specifications. So it actually consists of 3 types of components: places, transition and arcs. So these are the 3 components which actually forms the Petri net. So in Petri net we use the places. So the places are represented by circles, and then you have the transitions. The transitions are represented by rectangles. This is a place, transition, and then we have the arcs which actually represents the movement of the or the dynamics of the system. So we can actually have the arcs which actually connecting the places and transitions. So this actually is a place, so it actually shows one state, and the transition represents the change of state. So if there is a change in the state of a system, that actually can be activated by the transition block. So the transition block, when you activate, the place value will change, and that is actually shows that this has changed from this state to this state, or this has changed its place value from one to the other one. So this transition actually represents the transition from one place to another place, that is the place transition, and the arcs which actually represent, these are the basic building blocks for the Petri net. And then I mentioned the places represent possible states of the system. So these are the possible states, so we can represent this as P1, P2, etc., the possible states. So they will be having, we can have multiple transitions and multiple places, so P1, P2, P3, so this will be T1, transition 1, transition 2, like that. So you can have many number of places and transition in a Petri net. Then the transitions are events or actions which cause the change of state. So as I told you, so it is actually changing from this state to this state. So the transitions are the which actually makes the place value to change or the status to change from one to the other one. So every arc connects a place with a transition or a transition with a place. So that is the arc. So we have the state, transition and arc, place, transition and arc, and place actually represents the states P1, P2, P3, and transition represents the change from one state to other state. And the state of Petri net is defined by the marking. And again this marking, so the state of a Petri net or a state of a particular position is represented by a marking, say a black circle, a filled circle will be represented to show the status, whether it is in active mode or not will be shown by this black circle or filled circle, and this is known as tokens. So the tokens represent the basically the status. So the state will be represented by these tokens, and the change of state, this is the state of a particular place is shown by the token, and change of state by is denoted by the transfer of tokens. So when this state is changed to this one, this will actually show the transfer of this token. So we have a token here. So when I activate this T1, when this is activated, this token will be shifted to this one. So now this is in the active mode. So that is the change of position or the change of transfer of token. So every transition basically causes the change of the token or transfer of the token. So this change of state is denoted by movement of token from place to place and is caused by the firing of a transition. So the firing of the transition causes the token to move from this place to this place. So that actually represents the change of state of that particular function or the process. And the firing represents an occurrence of the event or an action taken, and the firing is subject to the input conditions denoted by tokens. So that is another important point, the firing is subjected to the initial conditions. Now if this is connected, this transition, suppose you have a transition like this T1, so we can actually have multiple places connected to this. So if it is given like this, so the firing of this token is subjected to the status of this position. So if there is a token in both these places, then only this transition can take place. So the firing is subjected to this condition. If this firing has to happen, then both this should be having the token. If there is only one token, then this transition cannot take place. That means these two conditions need to be satisfied for this transition to take place. So in this case, when I do the firing of this transition, both the tokens will be going to here and this will show a status over here. So this will be removed and this will be, there will be a token over here for when this is fired. If there is only one token, then this cannot be fired, there will not be any transition, there will not be any change in the status of that particular place. This is one situation, and another one is if you have like this and if you have this kind of a situation. So if you have only one token here, so these are simple Petri nets, so we do not have any place values as such at present. So we have a place connected to P1 connected to this T1 and P2 and P3, and if there is a token here available, so if this is the situation, then we can fire this transition because now it is already condition is satisfied that there is a token over here. So we can actually fire this transition, and when you fire this transition, both will be activated. So both the places will be activated. So this numbers does not really matter how many places are connected, the transition simply shows that from this status it has moved to this status. Any number of places can be connected to this transition, all this will be concurrently activated. So that is the condition for transition, and then after transition what is happening. So basically the Petri net, it has got this place, transition and arcs, and using place, transition and arc we can actually show many dynamic situations. So as shown here, so if this the condition for transition is basically has to satisfy the input conditions. So if there is a token, then only it can be fired, otherwise it cannot be fired. That means if this condition is not satisfied, there is no possibility for changing this status to another status. So that is the condition for transfer of tokens. So this is what I already explained, a transition is fireable or enabled when there are sufficient tokens in its input places. So there should be sufficient tokens in its input places to make a firing, and after firing tokens will be transferred from the input places to the output places, denoting the new state. So once you do the firing, the tokens will be transferred from the input to the output, which actually represents the change of state. Let me take an example and show you how to actually represent a scenario using the Petri net. So here we take again a simple example, an electronic fund transfer point of sale. So we know that we normally go to an ATM machine or an electronic point of sale, we have to insert the card and give the password, and then only it will accept the card and then transaction will take place. So how do we actually show this using a Petri net? This is a very simple example for use of Petri net. Petri net can be used for very more complex situations, but in order to understand the use of Petri net, we will take this example. So look at this diagram. So this is the initial status. So we have this initial token available and the card is inserted. The next is basically you need to give the password to the system. So here actually you can see there are 4 digits, so you can have 4 digits inserted. This is digit 1, then digit 2, this is the second digit, the third digit and fourth digit, and once all the 4 digits, then you can have an OK transition and then approve the transaction and then get the approved transaction out. So here you can see 4 digits need to be inserted, and everywhere you can see that this is a transaction. So 1 digit is considered as a transition. So you can actually give first digit once there is an input, this initial token is available, you can provide the first digit as a transition, and once you do this, then this status will come, that is there is a token over here, then you can insert the next digit, and once you have the next digit, then you will have your next transition, this is a third digit, then the place will come here and then keep on going to this loop. But in between, suppose you give 1 digit, then there is something called an OK button. So this OK button can actually be activated once you have a token over here. So this OK can be activated if you have a token at D1, but then it will get rejected because you have just entered only 1 digit, so it will not work. Similarly you can see the other OK buttons also, after the D2 also you can press the OK, but then it will not work because it will go to the rejected situation. So you need to have all the 4 digits and then press the OK button, and then only it will go to the approve stage and get the transaction done. So we can represent this in the 2 scenarios. We will show that one normal scenario where we enter all 4 digits and press OK, and then scenario 2 where we exceptional cases where we enter only 3 digits and press OK, what will happen. So how the dynamics of the system can be represented under these 2 situations. So let us look at this. So this is the first situation. So we have an initial token available at the position, so we already entered the card and then it is ready to accept the digit. So if you just give the transition, this transition, then you can see that the token has changed to D1. From initial the token has moved to D1, and then if you do the next transition, that is next digit, so you can see that token has moved to D2, and then one more digit it has moved to D3, one more digit has moved to D4, and then you have this OK button. So you have already given 4 digits and then press OK, it comes to that stage of token. So here you can have an option to reject the transaction or you can approve the transaction. After entering all the 4 digits, if you want to reject, then you can actually give this reject transition what is shown here, otherwise you can give the approve. Once it is approved, then the transaction will be approved and the token has come over here, and once the token reaches this point approved, again there will be one token available at the initial, that means it is ready for the next transaction. So that is the one loop of normal transaction. So you will be giving all 4 digits in succession and then press the approve and it will go to the approved situation, and again the token will be made available to the initial status so that you can actually start the operation again. So that is one condition. Now the second scenario where you press only 3 digit and press OK, then what will happen, we can actually show the same thing again using Petri net. So the first digit, second digit, then you have the third digit, and now if you press OK, it will go to the rejected and the transaction will be completed or it can be actually terminated. The token will be again made available to the initial one. Okay, so it will be rejected and it will go back to the initial one and you can actually start the process again. So this is the way how we can actually represent a simple transition or simple dynamics of a system using Petri net. I can show you a few more examples of using Petri net. So this is an example for a vending machine. The machine dispenses 2 kinds of snack bars, 20 and 15, and only 2 types of coins can be used, that is rupees 10 and rupees 5, and the machine does not return any change. There are multiple options for you to actually insert the coins and then get the output. So we need to show all those options and the dynamics using the Petri net. Here you can see that this is the vending machine Petri net. Here you can see the situations that you can actually deposit 5 coin or a 10 coin. So these are the options, and there are different loops. You can actually go through this loop. So you can go through any one of these loop, that you can go to the deposit 5, deposit 10 and deposit 5 loop, or you can go to the bottom one, deposit 10 and go to the 20 loop. So that way we can have different options. So we will just show a few cases how do we actually represent this kind of scenario using a Petri net. So scenario 1 is deposit 5, 5, 5, 5 and then take a 20 rupees snack bar, or scenario 2 is deposit 10, 5 and then take a 15 snack bar, and the scenario 3 is deposit 5, deposit 10, deposit 5 and then take a 20 snack bar. So we have multiple options. So all these options can be represented using the Petri net. So here is the Petri net for this particular scenario, and we have the token here. Initially it is 0, so it is ready for firing. So you can actually give a 5 or 10. You can see here that this 5 and 10 are actually can be fired, both can be fired because this 5 is connected to the 0 and this 10 is also connected. The initial condition for transaction is that there should be a token available at the circle marked the 0 or the place marked the 0. So here actually we can one token is available, therefore you can fire any one of these. So if you put a 5 rupee coin, then it will go to that 5 rupee loop, otherwise it will go to the 10 rupee. So here see we are actually putting 5, then it goes to that 5 token is available. Now you can actually go for this loop 10, or you can actually go for this also, because both are connected to that particular token, that place. So you can actually use any one of these. So here if you do the 5 again, then it will come to 10, and now you have an option of depositing 10 or depositing 5. So if you deposit 5 you can get a 15 rupees snack, or if you go for a 10 then you can take a 20 rupees snack. So here another 5 is given, so it is the 15 place is now have a value, or that status has reached. So there is an option of taking the 15 rupees bar, so you can actually activate this transition of 15 rupees. So this can be activated, or you can actually deposit another 5 and take the 20. So here another deposit another 5, now 20 is activated, so 20 place is active. So this is connected to the 20 transition of take 20, so you can actually activate this and take the 20 rupees snack, and then transition will go back to the place 0 will be activated, that place will be activated. The token will be transferred from 20 to 0. So once you take this 20 bar snack it will be transferred to 0. So that is how that one transaction take place. Now you have another option of 10, then 5, and then taking the 15 rupees snack, as you can see here. So the 15 rupees bar is taken and the token has come back to 0. The third option is you have 5 rupees deposit, then another 10 rupees deposit, and then 15, and then deposit another 5 and then take a 20 rupees snack and go to the next one. So these are the ways how you can actually represent the various transaction using Petri net. So again this is not a complex scenario, but of course you can represent complex scenarios also using Petri net. I have a few examples for the complex scenarios also. So here before going to those complex scenarios we will see those scenarios also, but the behavioral properties that we can actually analyze using Petri net are the reachability. Basically, can we reach one particular state from another. So we have a particular state of one situation and we want to reach another situation. So we need to find out what are the possibilities to reach that situation, whether we can really reach that situation from the present situation. So we can model that situations and then see by placing the tokens and the transition we have to analyze whether we can really reach that situation or not. So that can be done using Petri net. Another one is boundedness. Will a storage place overflow? So in some cases, like if you have what you call a storage or a location where you have multiple storage facilities and you are getting supply from different resources, so whether there is a possibility of an overflow of that particular storage, and whether what is the situation under which we need to place an order so that we make sure that the optimum usage of the storage space is done. So that scenario can actually be modeled using Petri net. The another one is the liveness of the situation, whether will the system die in a particular state. So whether it will go to a situation where we cannot get an output. So there may be some situations where we may not be intended, but still if you analyze some situation we will see that some situation we cannot get really an output, or somewhere actually it dies and no output can be done because the places the required transitions are not taking place because the conditions are not satisfied. Such situations also can be analyzed using Petri nets. Sometimes the things will happen at the same time and then system may have many local states to form a global state. So some systems will be having multiple input states and then these multiple input states will lead to a global state. So that also can be modeled using Petri net, and there is a need for concurrency and synchronization that also can be modeled and analyzed using Petri net. So these are the advantages of using Petri nets, and we will try to see how to model this kind of scenarios of overflow or the system getting into a situation where there is no output, or where how the concurrency can be modeled. So these cases we will see in the next class. I will take a few more examples to show the concurrency as well as the overflow situations and then ordering situations. So how do we actually model such dynamics using Petri net? This we will discuss in the next class. So till we meet, goodbye to all of you.